Hello. In this video, I will talk about how to model the insulated pipe in the EcosimPro, and also how to calculate the heat ingress from the outside to the pipe inside. In EcosimPro, we have pipe 1D components like this. So it includes the heat input port, but it has a limitation because we just put the heat ingress by a certain value. It cannot calculate the heat ingress from the outside to inside automatically. So that's why I developed this model. Okay, this is the schematic diagram of model. So in the center there is a flow channel which fluid can flow. So it is surrounded by inner wall, an insulation layer, and outer wall. So the heat ingresses from the outside to inside like that. So let's see in the EcosimPro. The flow channel represented is flow channel is represented by the tube 1D model, and also this is the inner wall, and this is insulation layer, and this is outer wall, and this is ambient. So the inner diameter is 20 millimeter, and outer is 26 millimeter. And the thickness of the wall is 1 millimeter, and length of the pipe is 1 meter. And also there's a 5 nodes in the tube. There are 5 nodes in the tube. So, and also the wall represented by cylinder. I put the 5 nodes in a axial direction, and I put 1 node in a radial direction as well. And I put inside and outside diameter as follows. And let's see the GL component. GL component represent the conduction. So we can put total thermal conductance in a watt per Kelvin unit. So you can calculate the value of the watt per Kelvin of conductance of your pipe layer. So you can just put it in here. And also in here you should set 5 nodes as well. This is outer wall, and this is the ambient. And also in here you ought to put 5 nodes in here. And then I put a valve in front of the tube, and I set helium as a working fluid, and I put source and sink. Okay, let's compile it. And then here's the experimental file of the model. So in here we can put the ambient temperature in Kelvin. So I put all the nodes to 300 Kelvin, and the source pressure is the 1.02 bar, and the sink is 1 bar. And I put initial temperature 300 as 300 Kelvin. Okay, and let's see the experimental monitor. Let's monitor it. Okay. So at the very first time, I did not open the valve, so all the components, all the inner wall and outer wall maintained 300 Kelvin. Okay, let's see. This table means the inner wall temperature from node 1 to node 5, and this is outer wall as well. and this is the mass flow rate through the valve, and this is the the heat ingress through the GL component in watt. Okay, so let's open the valve about the 50% of the position. Okay. Okay, so through the valve, the 0.0007 kilogram per second of the helium flow. Okay, and then let's flow colder colder helium about 200 Kelvin. Okay, and we can see the inner wall temperature going down, and we can see the heat ingress from the outside as well. Okay, okay, yeah, right. The inner wall temperature going down rapidly, right? Okay, let's see more. 500 second. Okay, okay. So the inner walls temperature saturated by 200 Kelvin almost, and also the outer wall temperature decreases. Temperatures decrease a little bit, like 0.3 Kelvin. Okay, and also we can see the heat ingress in the GL node, right? In here. Then we can see the 0.0009 kilogram per second of helium flows. Oh, quite interesting. Yeah. Let's see. 50 Kelvin of the helium flows suddenly. 2000 second. Let's see. Okay. Yeah. We can see the inner wall temperature decreases to al almost 51 Kelvin, right? And also in here, outer wall is almost 299.3. And in here, the GL component. Okay. So the each node has the almost 0.5 watt of the heat ingress. So the totally maybe 2.5 watt of the heat ingresses. Okay, yeah, thank you for listening. Yeah, that's all.